We thought we understood the universe, but when a Nobel Prize-winning physicist says, "This isn't our universe," you stop assuming the problem is small, because what if the issue isn't what we see, but how we are interpreting it, because something doesn't fit? Not in theory, in measurement, in numbers that should agree, but don't. And the deeper we look, the worse it gets. Less than 500 million years after the Big Bang, that is the time window we are observing with the James Webb Space Telescope. A time when the universe should still be in its early formation phase. Gas collapsing. First stars igniting, structures just beginning, like a construction site where only the foundation exists. But that is not what Webb is seeing. It is seeing galaxies, not small ones, not incomplete ones, but massive, structured systems already formed. Galaxies with masses approaching 10 to the 11th solar masses, existing when the universe was only a few 100 million years old. That should not be possible. That is the first crack. And it is not subtle, because our entire model of cosmic evolution is based on time. Given enough time, matter organizes, gravity pulls, stars form, galaxies grow. Remove that time, and complexity should not exist. That is the assumption. And for decades it worked. The standard model of cosmology, built on Einstein's equations and refined through observation, predicted how structure should emerge, step by step. From tiny fluctuations in the cosmic microwave background, mapped precisely by the Planck satellite, to the large-scale structure we observe today. Everything followed a sequence, until Webb. Because Webb is not guessing, it is measuring. Using infrared spectroscopy, it detects redshift, directly allowing us to calculate how far away galaxies are, and therefore how early in time we are observing them. That is a measurable quantity. Redshift values above z2 equals 10 correspond to a universe younger than 500 million years. And yet fully formed galaxies are already there. That is not an interpretation problem. That is a timing conflict. Now combine this with a second measurement, the expansion rate of the universe, the Hubble constant. There are two primary methods. One uses the early universe analyzing fluctuations in the cosmic microwave background. This gives a value of about 67 kilometers per second per megaparsec. The other uses the local universe observing type 1a, supernovae and galaxy distances. This gives about 73. Two methods, two precise measurements, two incompatible results. This is the Hubble tension, and it is real. Now we have a system-level problem, because the expansion rate determines the timeline of the universe, and the timeline determines how fast structure can form. If the universe expands faster, there is less time for galaxies to grow. But Webb is showing the opposite. Structure appears too early, as if formation is happening faster than allowed. That creates a contradiction inside the model itself. One part says, not enough time. The other shows, already finished. That should not be possible. Now there are explanations. One proposes that early black holes acted as seeds accelerating galaxy formation beyond expectations. Another suggests dark matter behaves differently at early times, clumping faster, forming structure earlier. A third proposes evolving dark energy changing the expansion rate over time. Each of these adjusts part of the system. But none resolve all observations simultaneously. Fix the timeline, and the expansion breaks. Fix the expansion, and formation becomes impossible. That is the conflict. And this is where the Nobel Prize connection matters. Because scientists like Adam Rees, who won the Nobel Prize for discovering the accelerated expansion of the universe, are directly involved in these measurements. At the same time, researchers like Wendy Friedman argue for refined calibration methods that could lower the local measurement, and teams analyzing Planck data linked to figures like George Efstathiou continue to support the lower early universe value. His team's supernova observations support the higher Hubble value. Other teams, using the early universe, support the lower value. Both are correct within their methods, both are based on real data, and both cannot be true at the same time. This is not disagreement. This is incompatibility. Now add Webb's observations, because Webb is not theory. It is direct observation. It is showing galaxies where they should not exist, at times where they should not be possible. That is the empirical fracture, a real observation that does not fit the model. Now consider what this implies. If galaxies can form this early, then either structure formation is dramatically more efficient, like a factory running at impossible speed, or our interpretation of cosmic time is incomplete, because early only exists relative to a timeline, and that timeline is model-dependent. This is the deeper layer. Because all measurements, redshift, distance, expansion, depend on how we interpret space-time. General relativity gives us equations, but it does not uniquely fix interpretation. There is flexibility, and that flexibility becomes visible under pressure. Webb is that pressure, because Webb is not adding noise, it is adding precision, and precision reveals inconsistency. Now here is the peak. If this is true, then the universe is not evolving too fast. We are reading its history incorrectly, and that shifts the entire system, because it means the expansion rate, the formation timeline, the structure of the universe are not wrong individually, but incompatible within our current framework. That is the consequence, not a small correction, a systemic fracture. Now there is a counterposition. Some argue these early galaxies are being misinterpreted, that their masses are overestimated, or their distances slightly miscalculated. If that is true, the tension weakens, the model survives. But even conservative corrections do not remove the problem. They reduce it, they do not eliminate it. And the tension remains, because it is not one anomaly, it is a pattern. Multiple observations, multiple methods, multiple contradictions, all pointing to the same place, the edge of the model. And this is where the meaning changes. Because this is not about galaxies. It is not about numbers. It is about interpretation. We thought we understood the universe. We thought the timeline was fixed, the structure predictable, the system coherent. But what Webb is showing is not chaos. It is misalignment, a reality that does not violate physics, but does not fit how we currently describe it. And that is more unsettling, because it means the universe is not breaking. Our understanding is, and that is why a Nobel Prize-winning physicist can look at the data and say, this isn't our universe, not because it changed, but because we are still learning how to see it. And every new measurement sharpens the contradiction, not resolving it, but exposing how fragile our deepest assumptions about reality might actually be.